Okay, and welcome back to part two. I'm thinking we're going to get this into 2 lectures instead of 3, regarding gluconeogenesis, glycogen metabolism, and pentose phosphate pathway. And we just wrapped up the first lecture overviewing gluconeogenesis. But one thing that we do need to do to wrap up gluconeogenesis is discuss the allosteric and substrate level control mechanisms, or / regulation. So let's take a quick look at the entirety of what we start with, where we start with glucose, and then, we go to glucose 6-phosphate, fructose 6-phosphate. I do not know why it's skipping around on me here. Let's see if I can. Fructose 6-phosphate goes to fructose 1,6-bisphosphate. Fructose 1,6-bisphosphate goes to phosphoryl pyruvate. And then phosphoryl pyruvate to pyruvate. And what we're doing here is skipping unregulated steps, just for brevity's sake. So what we just did is outlined glycolysis. So if we're only looking at glycolysis as regulated steps, let's refresh on how glycolysis is regulated. Going from glucose to glucose 6-phosphate is positively regulated allosterically by PI3K and AKT. And negatively regulated by glucose 6-phosphate. Fructose 6-phosphate going to fructose 1,6-bisphosphate is highly regulated. It's positively regulated by fructose 2,6-bisphosphate. It's positively regulated by AMP. It's negatively regulated by ATP citrate. It's the there's a variety of different things going on with that. And then if we look at phosphoryl pyruvate to pyruvate, it's positively regulated by fructose 1,6-bisphosphate. It's negatively regulated by acetyl-CoA. It's negatively regulated by ATP and also by alanine. And it's also negatively regulated by cyclic AMP-dependent phosphorylation. So let's go the other direction here really quick. Let's look at pyruvate. Pyruvate going to phosphoryl pyruvate via oxaloacetate is regulated by acetyl-CoA. Notice that is positively regulated by acetyl-CoA, whereas in glycolysis it was negatively regulated by acetyl-CoA. For going from fructose 1,6-bisphosphate to fructose 6-phosphate, we have two different regulators here of interest. We are negatively regulated by fructose 2,6-bisphosphate, and we're negatively regulated by AMP. Notice that both of those are negative regulators of gluconeogenesis, and they're positive regulators of glycolysis. And then, interestingly, going from glucose 6-phosphate to glucose is not allosterically regulated. However, it is regulated via substrate level control. substrate being glucose 6-phosphate. So, nearly all of the reactions of glycolysis and gluconeogenesis take place in the cytosol. So, if metabolic control weren't exerted over these reactions, glycolytic degradation of glucose and gluconeogenic synthesis of glucose would operate simultaneously, with no net benefit to the cell and with considerable consumption of ATP. If everything could happen simultaneously, we would just be burning ATP and we would not be getting anywhere. We wouldn't be getting good glycolysis and we wouldn't be getting good gluconeogenesis, regardless of metabolic need. So, this is prevented through a sophisticated system of reciprocal control. Reciprocal regulation, which inhibits glycolysis when gluconeogenesis is active, and vice versa. Reciprocal regulation of these two pathways depends largely on the energy status of the cell. So when the energy status of the cell is low, glucose is rapidly degraded to produce needed energy. And when energy status is high, pyruvate and other metabolites are utilized for synthesis and storage of glucose. Importantly, when blood glucose levels are low, gluconeogenesis is active, if you're looking for a single metric, which makes sense. In glycolysis, the three regulated enzymes are those catalyzing the strong exergonic reactions, hexokinase, phosphofructokinase, and pyruvate kinase. Like we've already mentioned before, the gluconeogenic pathway replaces these reactions with corresponding reactions that are exergonic in the direction of glucose synthesis. And that gives us our glucose 6-phosphatase, fructose 1,6-bisphosphatase, and pyruvate carboxylase, phosphoenol pyruvate carboxylase pairing. These are the three most appropriate sites of regulation for gluconeogenesis for the exact same rationale that the exergonic sites are the most appropriate sites of regulation for glycolysis. So what we just drew is the overall mechanism of regulation for gluconeogenesis. And control is exerted on all of the predicted sites, but in different ways. Glucose 6-phosphatase is not under allosteric control. However, because the Michaelis-Menten constant of the substrate, or for the substrate, glucose 6-phosphate is considerably higher than the normal range of substrate concentrations in physiological levels, the result is that glucose 6-phosphatase displays a near linear dependence of activity on substrate concentration, and this is called substrate level control, meaning the more of the substrate, the more active the enzyme. Acetyl-CoA, going back down to the bottom here, or the beginning, is a potent allosteric effector of glycolysis and gluconeogenesis. It allosterically inhibits pyruvate kinase, and it activates pyruvate carboxylase. Because it also allosterically inhibits pyruvate dehydrogenase, which is the enzymatic link between glycolysis and TCA cycle, the cellular fate of pyruvate is strongly dependent on acetyl-CoA levels. A rise in acetyl-CoA indicates that cellular energy levels are high and that carbon metabolites can be directed to glucose synthesis and storage. When acetyl-CoA levels drop, the activities of pyruvate kinase and pyruvate dehydrogenase increase, and flux through the TCA cycle increases, providing needed energy for the cell. So what we'll see is that as acetyl-CoA levels are high and we start to signal for storage, we're storing energy in the form of making glucose from metabolites, which will then get stored as glycogen or consumed. But also, acetyl-CoA will be the main substrate for lipid biosynthesis, or when we store energy in the form of fat. So in the next chapter, we'll pick up some additional rationale for why high levels of acetyl-CoA are a good indicator of sound energy status for the cellular environment. Now, fructose 1,6-bisphosphatase is another important site of gluconeogenic regulation. This enzyme is inhibited by AMP and activated by citrate. These effects by AMP and citrate are the opposite of those exerted on phosphofructokinase and glycolysis, providing another example of reciprocal regulatory effects. So when AMP levels increase, gluconeogenic activity is diminished and glycolysis is stimulated. An increase in citrate concentration signals that TCA cycle activities can be curtailed and that pyruvate should be directed to sugar synthesis instead. So I think one of the other really interesting points that we can look to here is that on the glycolysis side, you have a negative regulator here, which is a positive regulator here, and here we have a pair of positive regulators that are negative regulators. Lastly, let's take a look a little bit extra care to look at the fructose 2,6-bisphosphate as an allosteric regulator, because it's a very important allosteric regulator specific to both glycolysis and gluconeogenesis. So cellular levels of fructose 2,6-bisphosphate are controlled by phosphofructokinase 2 or PFK2 enzyme. And this enzyme is distinct from phosphofructokinase of the glycolytic pathway. It's also controlled by fructose 2,6-bisphosphatase. Remarkably, these two enzymatic activities are both found in the same protein molecule, which is really interesting. It's an example of bifunctional or tandem enzymatic activity. So you get dual enzymatic activities out of a single protein molecule. The opposing activities of this bifunctional enzyme are themselves regulated in two ways. First, fructose 6-bisphosphate, fructose 6-phosphate, the substrate of phosphofructokinase and the product of fructose 1,6-bisphosphatase, allosterically activates PFK2 and inhibits the F26-bisphosphatase. Secondly, the phosphorylation of cyclic AMP-dependent protein kinase of a single serine residue on the liver enzyme exerts reciprocal control over PFK2. So, overall, phosphorylation inhibits PFK2 activity and stimulates the F26-bisphosphatase activity. Now, let's spend one moment with substrate cycles. Because it's worth talking about. So, if fructose 1,6-bisphosphatase and phosphofructokinase acted simultaneously, they would constitute what's called a substrate cycle, in which fructose 1,6-bisphosphate and fructose 6-phosphatase became interconverted with a net consumption of ATP. You would just go back and forth between the two, consuming ATP perpetually. Because substrate cycles such as this appear to operate with absolutely no benefit to the cell, they were once regarded as a metabolic quirk and were referred to as feudal cycles. When I was an undergrad, they're called feudal cycles. More recently, substrate cycling has been recognized as an important mechanism for controlling metabolite concentration. So, the three steps in glycolysis and gluconeogenesis that differ constitute three such substrate cycles, each with its own particular metabolic rationale. Consider, for example, the regulation of the fructose 1,6-bisphosphatase fructose 6-phosphate cycle. As already noted, fructose 1,6-bisphosphatase is subject to allosteric inhibition by the fructose 2,6-bisphosphate. The combination of these effects should permit either phosphofructokinase or fructose 1,6-bisphosphate, but not both, to operate at any one time and should thus prevent feudal cycling. For instance, in the fasted state, when food intake is 0, phosphofructokinase, and therefore glycolysis, is inactive due to the low concentrations of fructose 2,6-bisphosphate. In the liver, gluconeogenesis operates to provide glucose in the brain. However, in the fed state, up to 30% of fructose 1,6-bisphosphate formed is recycled back to fructose 6-phosphate and then to glucose. Because the dependence of fructose 1,6-bisphosphatase activity on fructose 1,6-bisphosphate is sigmoidal in the presence of fructose 2,6-bisphosphate, the allosteric regulator, substrate cycling occurs only at relatively high levels of fructose 1,6-bisphosphate. So in the well-fed state, we do see substrate cycling. And substrate cycling, in this particular case, prevents the accumulation of excessively high levels of fructose 1,6-bisphosphate. So every now and then, under really high levels of substrate, as a protective mechanism, we'll actually consume, in a very well-fed state, some ATP, burn up some energy, and actually put some things back where they came from. Because pushing them all the way through the cycle may not be plausible. And we just need to get rid of some of those metabolites. So substrate cycling actually plays an important role when we have really high levels of substrate and we have energy to burn. It gives us a way to burn that energy off and put things back where they need to be. Now that we've wrapped up our discussion of the regulation of gluconeogenesis and its reciprocal control and substrate cycling, let's move on to the pentose phosphate pathway. We have a little bit of room here. Make a lot of room. So we can start this conversation by asking the question, can glucose provide electrons for biosynthesis? And remember, going all the way back to the very beginning of this semester, we talk about anabolic versus catabolic processes and how they're separated. That gets us to the core of our two reducing equivalents, NADH and NADPH. And typically, you think of glucose as producing NADH, which feeds into the electron transport and oxidative phosphorylation and the production of ATP. So the question here is, for biosynthetic processes, can glucose make NADPH, where these high energy electrons or hydride equivalents are used to form new carbon-carbon bonds, particularly in the synthesis of lipids. So let's talk about this. Cells require a constant supply of NADPH for reductive reactions, which are vital to biosynthetic purposes. A lot of this requirement is going to be met by glucose-based metabolic sequences previously called the pentose phosphate pathway. I still call it the pentose phosphate pathway, but it's also been called the hexose monophosphate shunt or the phosphogluconate pathway. For the sake of brevity and clarity, I'm going to just refer to it throughout as the pentose phosphate pathway. So in addition to providing NADPH for biosynthetic processes, the pentose phosphate pathway produces ribose 5-phosphate, which is going to be essential for nucleotide or nucleic acid synthesis. Several metabolites of the pentose phosphate pathway can also be shuttled back into glycolysis for efficiency's sake. So the pentose phosphate pathway operates in the liver and in adipose cells. And yes, adipose cells are fat tissues. The pentose phosphate pathway begins with glucose 6-phosphate, which is our 6-carbon sugar, and throughout the sequence is going to produce 3 carbon, 4 carbon, 5 carbon, 6 carbon, and even 7 carbon sugars. As we'll see when we get into it, 2 successive oxidations lead to the reduction of NADP plus to NADPH and the release of carbon dioxide, which will help drive the reaction as a decarboxylation. And then 5 subsequent non-oxidative steps produce a variety of carbohydrates, some of which may enter glycolytic pathways. The enzymes of the pentose phosphate pathway are particularly abundant in cytoplasm of liver and adipose cells, which is where this takes place. These enzymes are largely present, they're largely absent in muscle, where glucose 6-phosphate is utilized primarily for energy production via glycolysis and TCA cycle. So in places where there's greater degree of specialization for the consumption of glucose 6-phosphate for energy production, such as muscles and neurons, you're not going to see pentose phosphate taking place. These pentose phosphate pathways and enzymes are located primarily in the cytosol, which is the site of fatty acid synthesis as well, a pathway which is going to be heavily dependent on NADPH. So, makes sense if we're going to be making this NADPH for synthesis of fatty acids that you would want them to be in the same place. So, what we're going to do is draw the first steps, talk about it, and then draw the following steps. So, starting out, we've got our glucose 6-phosphate. And we're going to draw these as open chain carbohydrates. 1, 2, 3, 4, 5, 6. Let's see here. So here we have our glucose 6-phosphate. Which is our starting point. And we're going to have a sequence of 2 steps in which water is incorporated and NADP plus is converted to NADPH plus a proton. And this is going to give us 6-phosphogluconate. And you may notice right away that the only difference is the oxidation of the first carbon. Everything else is the same. So I'm going to go count up our carbons here. 1, 2, 3, 4, 5, 6. Put our hydroxyls on. Our hydrogens on. And this is our 6-phosphogluconate. And this is going to be our first step and our second step combined to make 6-phosphogluconate. And then in our third step, we're going to have another oxidative step, making another equivalent of NADPH. we'll also have a decarboxylation, which will help drive the reaction. And this will yield ribulose 5-phosphate. So ribulose 5-phosphate looks like this, where we're going to have 5 carbons because of the decarboxylation. 1, 2, 3, 4, 5. Oh my goodness. Why on earth? Okay, we're going to get this down eventually. Eventually, probably about the time I stop making these videos, I will actually learn how to use a tablet. Unfortunately, my PhD is not in use of tablets and old dogs and new tricks and all of that. Okay, here we go. Here's a ribulose 5-phosphate. And this is going to be our third step. Now, what's really important is that from the ribulose 5-phosphate, we're going to have reversible steps that take us to 2 different avenues, depending on whether it's step 4 or 5. But before we get into that, let's talk about steps 1, 2, and 3. So, the pentose phosphate pathway begins with 2 oxidative steps, which includes the enzymes of action 1, glucose 6-phosphate dehydrogenase. So, and the second being gluconolactonase. I'm not going to have you remember this necessarily. It's not the enzymes of this aren't going to be something you're tested on. And then the third step, which we're seeing with our second conversion of NADPH, is going to be 6-phosphogluconate dehydrogenase. And it's going to be what ultimately yields our ribulose 5-phosphate, along with another equivalent of NADPH. So this gets us 2 oxidative steps and gets us our biosynthetic reducing equivalents in the form of NADPH. And then from ribulose 5-phosphate, we have the ability to make 4 subsequent non-oxidative reactions. And these non-oxidative steps are primarily for the generation of odd-sized carbohydrates, including ribose 5-phosphate, which is essential for our nucleic acid synthesis. So what this looks like is a little bit convoluted. So I'm going to give us some space. And we're going to go from the ribose 5-phosphate. You know what? I can actually just bring it over here. Come on, come down. And move you over here. There we go. I don't have to redraw the ribulose 5-phosphate. So ribulose 5-phosphate, if it goes through the reaction sequence from 4, phosphopentose isomerase, will go up through the top pathway, and if we go through the bottom pathway, number 5, we phosphopentose epimerase. So what's the difference? Well, the isomerase is going to make ribose 5-phosphate from the ribulose 5-phosphate initially. And it's going to look like this. Let me make a little bit of space, give us a little bit of room here. You can see right away that we have an oxidation on the first carbon and a reduction on the second carbon. 2, 3. All of the hydroxyls of the ribose 5-phosphate are on the same side. And then from here, we can form a cytoheptulose 7-phosphate where we add 2 more carbons, erythrose 4-phosphate where we have a 4-carbon structure, and this just is a passing of carbon units back and forth. So to make this make sense, let's do the epimerase side first so you can see what's taking place. So we're going to start with the first step of the phosphopentose epimerase reaction from ribulose 5-phosphate, and it looks like this. If my pen will work. There we go. Here we go, and this is our xylulose 5-phosphate. And what's going to happen is we're going to get a swap in reaction 6. Where carbon units from the xylulose are transferred to the ribose. And we're going to get a 7-carbon sugar on top. And we're going to get glyceraldehyde, a 3-carbon sugar, on the bottom. So I make a little bit of room because I need to draw 7 carbons. 1, 2, 3, 4, 6, 7. Maybe a little bit more room. And right away, you can see structurally, elements of the xylulose have now been added to the top of the ribose through nucleophilic attack. And this is going to lead to a new hydroxyl on what was the 1-carbon of the ribose and is now the 3-carbon of the cytoheptulose. You can see that none of the hydroxyls of these 3 hydroxyls have changed fundamentally in terms of their location. And this is cytoheptulose 7-phosphate. And below, now that we've removed the top 2 carbons from xylulose 5-phosphate, we're going to have glyceraldehyde 3-phosphate on the bottom. A 3-carbon sugar. And this is our 6th reaction. And then we can see yet another exchange where we now move 3 carbons from the cytoheptulose to form erythrose 4-phosphate. And we're going to transfer those 3 carbons to the glyceraldehyde, forming fructose 6-phosphate. So we're going to take those top 3 carbons off the cytoheptulose and end up with erythrose 4-phosphate. 2, 3, 4. Get our aldehyde on, and then we just need our 2 hydroxyls. And we're going to take those 3 carbons from the top that we pulled off the cytoheptylose 7 phosphate, and we're sticking them on the glyceraldehyde, making our fructose 6 phosphate. Six. And yes, this is, reminder, an open chain variation on how to illustrate fructose 6 phosphate, because I know we have been traditionally doing it in a more stable form, but when you're moving carbons around in biosynthetic pathways, enzymatically, it happens in the open ring format. And then finally, in the last step, we can get another xylulose 5-phosphate, which was our initial reaction number 5 product, to come in and react to form a glyceraldehyde 3-phosphate. And what we now have are, in our fructose 6-phosphate and glyceraldehyde 3-phosphate, are glycolytic intermediates. So, if we carefully zoom back out, and then over to the beginning, we can see that pentose phosphate pathway has our 2 oxidative steps where we go from glucose 6-phosphate to 6-phosphogluconate to ribulose 5-phosphate, yielding 2 equivalents of NADPH, which will be very important for biosynthesis. And following those 2 oxidative steps, ribulose 5-phosphate goes 2 ways, via phosphopentose isomerase and phosphopentose epimerase, yielding ribose 5-phosphate and xylulose 5-phosphate, which can then combine through moving the carbon subunits around to form cytoheptylose 7-phosphate, a 7-carbon sugar, glyceraldehyde 3-phosphate, our 3-carbon unit, which also feeds into glycolysis, and then these can swap to form erythrose, a 4-carbon carbohydrate, which can then undergo a second reaction with xylulose 5-phosphate, giving us another fructose 6-phosphate and glyceraldehyde 3-phosphate. And what we have here is a pool of 3, 4, 5, 6, 7 carbon carbohydrates, which can contribute to nucleotide synthesis, as well as, once we've harvested some energy in the form of NADPH for the form of biosynthetic energy, we can now take the rest of it and shuttle the rest of it into synthetic pathways and back into glycolysis to abstract as much energy as possible so nothing's wasted. So this is the mechanism by which glucose can give us energy for biosynthesis in terms of high energy reducing equivalents, NADPH. And this is going to be very important in the next chapter when we talk about lipid. Maybe it's not the next chapter. I think we talk about lipid catabolism first, the use of lipids for generating energy, and then in the following content we talk about lipid biosynthesis. So regardless, that is going to be it for gluconeogenesis and for pentose phosphate. Let me see if there's anything else we should talk about. I think that'll do it. So, that said, I'm going to load this up for y'all, and I'll be talking to you about lipids and lipid metabolism shortly. Fatty acid catabolism and lipid biosynthesis coming up next.